Today we will start the chapter Periodic Properties. The periodic table is the framework upon which much of our understanding of inorganic chemistry is based. In this chapter, we will provide the basic properties that you will need for the detailed discussion on main group elements in later chapters. Long form of periodic table. In the modern periodic table, the elements are arranged in order of their increasing atomic numbers, that is, the number of protons. There has been several designs of the table over the years, but the two most common designs are the long form and short form. The long form of periodic table shows all the elements in numerical order. However, the long form is a very elongated and cumbersome diagram because elements from lanthanum to ytterbium and from actinium to nobelium show similar chemical behavior. The short form cleverly displays these two sets of elements in rows below the remainder of the table and the resulting space is closed. The new compact short form of table is shown in the figure 2.2. The long form of periodic table consists of horizontal rows are called periods and vertical columns which are known as groups. A period is comprised of a series of elements, the atom which possesses the same number of shell, that is the principal quantum number, which is represented by n. The number of elements in each period correspond to the number of electrons required to fill orbitals as shown in figure 2.3. In a particular period, the principal quantum number of the p orbital is same as that of s orbital, whereas the d orbital are 1 less and f orbitals are 2 less. The main group corresponds to the in which s and p orbitals are being filled. Let's see the picture 2.3 in which the electron orbital filling sequence is shown. In the periodic table, there are 7 periods and each period starts with the new principal quantum number. It is important to mention that the first 6 periods are full and contain 2, 8, 8, 18, 18 and 32 electrons respectively, while the 7th period is incomplete and contains 26 elements. It has a maximum capacity of 32 elements. The first 3 periods contain 2, 8 and 8 elements are known as short periods, while the next 3 containing 18, 18 and 32 elements are known as long periods. The vertical columns are known as groups. Each group consists elements of similar electronic configuration. For example, in all group 1 elements have an outer electron that is ns1 where n is the principal quantum number. Although elements in a group have similar properties, it is very important to realize that every element is unique. For example, nitrogen and phosphorus are elements of same group. Nitrogen gas is very unreactive and phosphorus is highly reactive and spontaneously catches fire in the air. There are in total 18 groups in the long form of periodic table according to the recommendations of IUPAC, that is International Unit of Pure and Applied Chemistry. The group of the elements are numbered from 1 to 18. Earlier the groups were numbered from 1 to 8 as A and B groups. IUPAC has replaced the old system of using a mixture of Roman numerals and letters. This notation caused some confusion because of differences in numbering between USA and rest of world. As an example, in USA, the third B refers to the group containing scandium, whereas in the rest of the world, this designation was used for the starting from boron. Group 1 and 2 and Group 3 to 18 represent the main group elements. Group 3 to 11 are classified as transition metals. In the transition metals, the d orbitals are progressively filled. We shall be focusing in the course of our chemistry on the main group elements. The elements of group 12, although included in the transition metals, have a very different chemistry. Some of the group have got special names. For example, Group 1 is also known as alkali metals. Alkaline earth metals are referred to second group. Chalcogens are referred to group 16 and halogens are referred to group 17, and noble gases are belonging to the 18th group. The element of 11th group are known as coinage metals. The elements corresponding to the filling of 4f orbitals are known as lanthanoids, and those corresponding to 5f orbitals are known as actinoids. Earlier, these were named as lanthanides and actinides, but the ending "ide" not justified as is generally used in the end of anions. Example: oxide or chloride. Initially, IUPAC suggests the name of lanthanons and actinides. However, later this was not finally accepted as the ending "on" preferred only for nonmetals. Example: boron, silicon, whereas the lanthanides and actinides metallic in nature. Finally, the word lanthanoid and actinoid are recommended and should be strictly followed. Now we will start S, P, D and F block elements. The long form of periodic table can be conveniently divided into four blocks: S block, P block, D block and F block. S block elements are those elements in which the last electron enters the s orbital of their outermost energy levels are called S block elements. There are two groups in this block with electronic configuration NS1, that is alkaline metals, and NS2, alkaline earth metals. The general configuration of the S block elements is NS1 to 2. Second, we will discuss the P block elements. The elements in which the last electron enters the p orbital of their outermost energy level are called P block elements. The general configuration of P block elements may be written as NS2, NSP1 to 6. All the elements of group 13 to 18 constitute the P block elements. Now we will discuss D block elements. The elements in which the last electrons enters the d orbital of their penultimate last but one energy level constitute D block elements. These elements are called transitional metals. It is because these elements symbolizes a change in character from the metals on extremely left on the side to non-metals on extremely right. Thus, the elements lie in between S and P block elements and form 10 groups. These groups are named group 3 to 12. The general electronic configuration of D block elements may be represented as N-1 D 1 to 10 NS1 or 2. The D block elements contain 3 complete rows of 10 elements which involve the filling of 3d, 4d and 5d orbitals respectively. Elements starting from scandium to zinc for the first transition series, elements starting from yttrium to and ending with cadmium constitute the second transition series, while elements starting from lanthanum, hafnium to mercury is called third transitional series. Now we will discuss F block elements. The elements in which the last electrons enters the f orbitals of their atoms are called F block elements. The last electrons enter into the third of the outermost energy level, that is N-2. There are two series in this block of elements are separately placed at the bottom of periodic table. The first series starts from lanthanum having atomic number 57, and the elements present in this series are known as lanthanoids. The second series starts with elements actinium atomic number 89 and ends up with the element having atomic number 103 represented by the symbol Lr. The elements of this series are known as actinoids. The general electronic configuration of these elements may be represented as N-2, F1 to 14, N-1, D0 to 1 and NS2. Now we will start the effective nuclear charge and Slater's rule. We have already discussed that in a multi-electron atoms, the electrons in the outermost shell do not experience the full effect of nucleus. This is primarily because of the intervening electrons that come in the way between the nucleus and the outermost electron of the atom. In other words, the inner core of electron set as a barrier between the nucleus and the outermost electrons. As a result, the outer electrons experience only a part of nuclear charge. The actual charge felt by the outermost electron is called effective nuclear charge, which is lower than the total nuclear charge. Since the inner electrons serve as a shield or a screen, this effect is known as screening or shielding effect. Thus, the effective nuclear charge Z star can be expressed by subtracting the shift screening effect from the outer electrons from the actual nuclear charge. The formula for calculating the effective nuclear charge is by subtracting the actual nuclear charge from the screening constant. In 1930, J.C. Slater proposed a set of empirical rules to calculate the effective nuclear charge. These rules are solely based upon the penetration power of the various orbitals. We have already learned in the chapter 1 that is s electron stands to the shield the nucleus more effectively than the p electrons, which in turn will shield the nuclear electrons more efficiently than d electrons. Thus, for a given value of n, the screening constant s varies as the much larger than s, then to p, and then to f. Now let's start the periodic properties. Atomic properties, which are used to explain the periodicity of chemical and physical properties, must also be periodic in nature. We would expect atomic properties to be related to the observed periodicity in the electronic configuration of atoms. We shall examine four of the important atomic properties that are most useful in explaining the chemical and physical properties. These are atomic and ionic radii, electron affinity, ionization energy, and electronegativity. Now let's start atomic and ionic radii. Atomic size. One of the most important systematic properties is atomic and ionic radius. We have learnt in the previous chapter that electron can be defined only in terms of probability, and therefore there is no real boundary ascribed to an atom. In other words, the electron cloud around the nucleus do not have sharp defined boundary. Thus, atoms and ions cannot be regarded as hard balls. How can then we define the size of atom or ion? There are actually four ways to determine the size of atom. To some extent, they give different values. One of the simplest methods to define the atomic radius is to measure the distance between the nucleus and outermost shell of an atom or an ion. Let's take a simple homonuclear atomic molecule such as chlorine. The radius of chlorine atom can be determined experimentally by dividing the distance between the centers of two atoms in chlorine molecule by 2. The distance is 2 angstrom, that is 200 picometer. So the radius of chlorine is 100 picometer. The distance is also known as covalent radius because the atoms are held together by a covalent bond. Similarly, the CC distance in the diamond is 1.54 angstrom, also 154 picometer. So the radius of carbon is 77 picometer. In order to test the accuracy of this method, we can add them together to estimate the carbon chlorine distance come out to be 177. The distance is in closest agreement with the experimentally determined distance of 176 picometer. The radius of an atom is calculated by measuring the distance between the center of two nucleus in a molecule with the help of X-ray diffraction or spectral studies. Thus, in case of homonuclear diatomic molecules, the covalent radius is defined as the one half of the distance between the center of nuclei internuclear distance of two similar atoms bonded in a molecule. Similarly, in a heteronuclear diatomic molecule, the singly bonded covalent radius of an atom can be calculated by knowing the intermolecular distance between the two nuclei and covalent radii of other atom. For example, the internuclear distance between the iodine and chlorine is the Ci bond, that is 2.32 angstrom, which is calculated by radius of iodine plus radius of chlorine, that is 2.32 angstrom. Radius of iodine plus 1 angstrom is equal to 2.32 angstrom. The atomic radius of chlorine is 1.0 angstrom, that is calculated earlier. So the radius of iodine is 1.32 angstrom. Thus, the covalent radius of iodine is 1.32 ampere. This approach of determining the radii of atoms applicable only in the molecular compounds of an element that exist as singly bonded. The atomic radii of an atoms which do not form diatomic molecules with single bonds are calculated by indirect method. For example, the single bond of radii of nitrogen and oxygen cannot be obtained from the bond length in the triply bonded and triple N2 molecule or doubly bonded O double bond O2 molecule. This is because these molecules contain multiple bonds. The single bond atomic radius of nitrogen can be obtained indirectly. For example, the internuclear distance between C and N in CH3NH2 has been found to be 1.47 angstrom. We know that the atomic radius of carbon in diamond is 0.77 angstrom. Therefore, the atomic radius of nitrogen in CN bond is 0.70 angstrom, that is 1.747 minus 0.77. The simple rule of evaluating the atomic radius is true in cases where the bonds formed between the atoms and the are singly covalent. The difference in the electronegativity of bonded atoms is not so large. However, in some cases, if there is a large difference in their electronegativities, Shoemaker and Stevenson proposed a new equation for calculating the covalent radius. That is, the radius of an atom AB is calculated by adding the radius of B plus adding the radius of A by subtracting the electronegativities of A and V and multiplying the constant C, where RAB is the internuclear distance between A and B. RA and RB are covalent radii. Xi A and Xi B are the electronegativities of A minus B respectively, where C is a constant and have a value of 0.06 for second period, 0.06 for third period, 0.04 for fourth period, and 0.02 for fifth period of p block elements respectively. The value of covalent radii of different elements of S and P block elements are shown in the table. A careful inspection of the table 2.1 reveals that for N, the main group elements, the atomic radii increases going down the group in the periodic table and decreases going along the period. This can be easily explained. In going from top to bottom of the periodic table, the outermost electrons are placed in orbitals with higher and higher value of principal quantum number. The higher the principal quantum number, the larger is the radius of the and the charge of the nucleus increasing going down a group. In the effective nuclear charge, that is the actual charge experienced by the outermost electron, does not increase as much. For example, the atomic number of lithium is 3 and the atomic number of potassium is 19. The positive charge in the nucleus of potassium atom is over 6 times as large as